continuous time exponential signals, we have discrete time exponential signals and associated sinusoidal signals. Okay, which if you expand those complex exponentials in a Euler's form, you can bifurcate into real and imaginary parts, and you can get sinusoids out of it. In continuous time, an important signal in discrete time is again the complex exponential signal or sequence, okay, because it's discrete, which is defined as x of n as C alpha n, and C and alpha are in general complex numbers. Now, the analogy, if you have to write this discrete sequence in a similar form to what we discussed for continuous form was, if you recall, for the continuous time exponential, we expressed this in the past two videos as some constant C e to alpha t or at. Okay, that was the form of the continuous time exponential signals. And here again, alpha a and c could be real. Okay, they could be complex in general. Okay, a could be purely complex. For example, if it is purely complex, then if you recall, x of t was periodic. Okay, if you have to draw an analogy, I mean, you have to express the discrete sequence in a similar form as continuous time signal, then this alpha of raised to power n can be written as an exponential sequence as e to the beta n. Okay, so again, you have a constant with exponential beta n. N is a discrete time index over here, where alpha is simply replaced by e to the e beta. Okay, beta could be real, it could be positive, it could be negative, and it gives certain characteristics, defines the behavior of this complex exponential sequence, whether it is growing with increasing time index n, or it decays. Okay, just like we saw that in the real signals in the continuous time exponential signals, where a was real. Okay, with both a being positive or negative. And then again, for beta, if beta is complex, then you can derive sinusoidal signals if you expand this in Euler's form, and it gives again a special characteristics to the behavior of this exponential sequence, depending on whether beta is purely imaginary, okay, if beta is real, positive or negative. So let's consider these cases one by one. Now, for real exponential signals, both beta and c over here are real. That means alpha is real, c is real. So if c and alpha are real over here in the complex exponential sequence, then we can have one of the several type of behavior as illustrated in the figure below. So we have four behaviors, as you can see in A, B, C, D. Now, if c and alpha are real, you can have the magnitude of alpha greater than 1. And if that's the case, if the magnitude of the signal, then the magnitude of the signal is going to grow exponentially with n. Okay, but if alpha is less than 1, then we have a decaying exponential. So over here, let's say for part A, this is your discrete sequence. If alpha is greater than 1, which implies the magnitude of alpha is greater than 1. That simply means, for example, you have x of n is of the form. X of n is of the form. Let's assume C to be real, and let's take that as unity. Let's take the case as 2 raised to power n. Okay, that's the first case. Now this signal, if I have to see its behavior with evolution of the discrete time index as n goes to infinity, okay, if n becomes large, then this sequence becomes infinitely large. So I would expect the samples to grow with discrete time index n on the right hand side. As n increases, the exponential behavior and the magnitude of the samples is going to increase exponentially. Okay, so this is what is being shown in this in the first case, where alpha is greater than 1. Now in the second case, if alpha is a fraction, okay, it is positive. Alpha is still positive. Alpha is real, positive, but it's a fraction which is less than 1. Then in that case, let's take another example. So if I let n approach to infinity for a very large time index, I want to see the behavior of this sequence, and let's say x of n that we are considering is of the form half half n, right? So it's like this. Alpha is still positive but less than 1. C can be taken as unity for convenience over here. So you see what happens is that as n grows, the sequence approaches to 0. Okay, and that's the case over here. So it's a decaying exponential. It's a decaying exponential. So as n discrete time index becomes large, the sequence, the magnitude of the samples in the sequence with increasing n becomes small. Okay, but it's the other way around for the negative indices of n. So for n less than 0, this becomes basically 2 minus n, right? And you can also express this as 2 minus n. And if you can see that for n being negative, this becomes, for n less than 0, this is 2n, right? This is 2n. So it grows on the other side, right? So for n being less than 0, let's say n equal to minus 1 or minus 2, minus 3. So minus 3 is 2 raised to the power 8, then minus 4 is 2 raised to the power 4. So it's growing on the other side, it's growing on the left side, but it decays as n approaches infinite on the right hand side. Okay. Similarly, in the we are considering the cases where C and alpha both are real. So your sequence, the samples that we are considering are real samples. These are real samples. Okay, the magnitude is real. Okay, so well, the magnitude of the complex sequence is also real, but there is no phase part. The phase part is 0. Okay, so it's a real sequence. The third case is when alpha is again a fraction, but it has a negative sign, so it's not positive. So in third case, what you can do is to see what happens if n goes to infinity for a sequence, let's say minus 1 by 2 to n. Okay, so alpha, you can see over here, alpha is less than 0, but it's greater than minus 1. Okay, for the third case. So what happened is that first of all, you will see that the samples are going to alternate. The signs are going to alternate. So between the successive samples, the samples and the sign of the samples is going to alternate. Okay, why? Because you see, for example, minus 1 over 2 whole squared is 1 by 4, but minus 1 by 2 cube is minus 1 over 8. Okay, so there will be fluctuations in the samples. Okay, the sign, because of the sign. Then again, since magnitude of alpha is less than 1, we expect a decaying exponential behavior, like in part B. So there will be a decaying exponential behavior, but this decay will be alternating its sign, okay, because it's not positive, it's negative. Okay, so as n approaches infinity, again we have on the right hand side the sample, they must go to 0, right? So as n goes to infinity, over here on the right hand side, the magnitude of the samples, or the amplitude of the samples, it's decaying. So it's again a decaying exponential, but the samples are just changing the signs. The successive samples are alternating the signs. Okay. All right. Then the last part is the last consequence of C and alpha being real. Last possibility is that alpha is less than minus 1. So in that case, let's consider an example that alpha is minus 2. Okay, so limit n goes to infinity for part D, and let's take this, the power to n, the discrete time index. So what happens is that again you will see that there will be the signs are going to alternate, but this the trend is going to blow up. Okay, as n becomes large, we will have a growing exponential, again with alternate signs. Okay, because for example, minus 2 raised to the power 1 is minus 2, then minus 2 raised to the power 2 is 4, minus 2 raised to the power 3 is minus 8. So there will be alteration of signs between successive samples. Okay, so again it's a growing exponential as n is increasing. Okay, but on the left hand side, where n is less than 0, the samples are going to decay. It will be 0, right? So but the evolution is always considered towards n increasing on the positive axis, where n is positive. So this grows, okay, this grows to then. So furthermore, if alpha is positive, all the values of C, alpha, n are of the same sign. Okay, so in both these cases, in part A and part B, alpha, you see, alpha was positive quantity, alpha was a positive quantity. So there was no alteration of sign. It's just the either the sequence, the sample of the sequence, they grow or they decay depending on if alpha is less than one. So, but in the third and fourth case, the other two possibilities, but where alpha is negative and then the sign of x of n alternates, right? So note also that if alpha is equal to 1, well, if alpha is equal to 1, then this is pretty much a constant, right? This is nothing but C. And whatever is the value of C is, that's what we have. So then x of n is a constant sequence, all the samples being C. Whereas if alpha is minus 1, then again it's a constant, but the constant is going to alternate. The magnitude of the samples is the same, it's C, but it's going to, the phase is going to alternate 180 degrees. So x of n is going to alternate between plus minus C. Okay, so if that is the case, if alpha is minus 1, then what happened is that this becomes minus 1 to the power n, and what you're going to have is plus C minus C, and this trend continues. Okay, so for odd indices it's minus C, for even indices it's positive C, and this trend basically continues. It's either C, it's minus C, and then the samples are going to alternate the signs. Okay, so it's C plus minus C, and this trend continues forever. Okay, all right. Now how you can derive sinusoidal signals is again another important complex exponential is obtained by using the form given in the following equation and by constraining beta to be purely imaginary. So how you can obtain sinusoidal signals from the generic form of the exponential sequence is by constraining alpha to be purely imaginary, or you let beta over here, since alpha is purely imaginary, beta is only can only take complex values, no real part. Okay, so beta is, for example, is of the form j omega naught. Okay, so beta is j omega naught, purely imaginary. Over here, beta is j omega naught. And if that is the case, you can always expand this in terms of in Euler's expansion. Okay, so over here, the other thing to note is the magnitude of alpha, because this okay, alpha over here is e to the beta n. Remember, okay, and if beta is purely imaginary, which is the case over here, then alpha is e to the j omega naught n, and you can figure out that the magnitude of alpha is 1. Okay, so magnitude of alpha is 1. Why is that the case? Because cosine square plus sine square is 1. You can expand this. I mean, what I'm saying again is that this is equal to cosine omega naught n. Okay, and then there's an imaginary part to it plus j sine omega naught. So the imaginary part is the sine omega naught. Okay, if you take the magnitude, then you will have sine square plus cosine square under root, and that's 1. Okay, so the magnitude of alpha is 1 in that case. Specifically consider this, and as in the continuous time case, this signal is closely related to the sinusoidal signal, which is again the real part of x of n. Okay, so if we take n to be dimensionless, you can guess what are the dimensions of omega naught and phi are. So the difference in discrete time sinusoid is that omega naught is not in radians per second, because n is dimensionless. So that again put a constraint on omega naught to be radians. So omega is a dimensionless quantity, and this is the digital frequency. It's not a analog frequency, which is analog angular frequency, if you recall, is in radians per second. This is digital frequency, and it is radians. Okay, similarly phi is also constrained to be radians over here. It's not it won't be again I mean you can only add radians to radians, right? So you don't have omega naught. This is the difference. So in discrete time sinusoids, omega naught is not in radians per second, it's in radians. Okay, phi is in radians in both cases. Okay, so there are 3 examples of sinusoidal sequences that are shown on the figure on the right. Now, if you recall, I said that okay, if your sequence, if you have a continuous time signal xt, in which the exponent is purely imaginary, as the case is over here. if the exponent is like this, then this signal is always periodic. Why? Because it consists of cosine and sines. And this omega naught is in radians per second. This omega naught is in radians per second. That's another difference. So you see, the analogy cannot be derived almost in the similar manner as we talked of for the continuous time exponential signals. The discrete time sinusoidal signals or complex exponential sequences. Another difference is that besides the dimensions of frequency, is that they are not periodic. Okay, they are not necessarily periodic. The discrete time sinusoids, or discrete time exponential sequences are not unconditionally periodic as compared to complex continuous time exponential signals. These are always periodic. This is always periodic. Why? Because this can always be expanded in cosine and sine, and cosines and sine in continuous time domain are always periodic. So your complex exponential signal is always periodic, but that's not true for your discrete time case. Why? Just have a look. You see this, the first sequence is cosine 2 pi n by 12, which is periodic. You can find the period. Again, in the second case, this is 8 pi n 31. Just look at the how this sequence, the samples in the sequence look like. Okay, and you can find a pattern that is repeating. So you can find the smallest capital N, that is again an integer, that gives you the period, the number of samples after which this is going to repeat. But the third case is not periodic. Okay, because you cannot find a small n. In order for the sequence to be periodic in discrete time case, is that x of n should be equal to x of n plus capital N, and you should be able to find a real quantity, a positive real quantity, capital N, that happens to the period. So delaying the sequence or advancing the sequence by capital N should give you back your original signal. If that is the case, then for that particular n, the sequence is said to be periodic. So the only constraint is that n should belong to positive integers, right? Because n is integer, so n, capital N, also has to be integer and also a positive integer, right? So for this case, what happens is, if you consider the sequence cosine, and for a moment you say that, okay, you believe that this is periodic, okay, and then you argue that, okay, if that is the case, then the equality should hold, that then I should be able to find the period capital N for which this is true. So let's try to find out that if we can determine this period. So this will be small n plus capital N whole by 6. So what we are interested is to find if this equality holds for this particular sequence. Now, in order for this equality to hold, the right side of the equation can be written as cosine of n by 6 plus capital N by 6, and if you can figure out, the constraint will be that this capital N by 6 should be equal to an integral multiple of 2 pi k, right? Where k is again an integer, right? It could be 4 pi, it could be 6 pi, doesn't matter. The problem is that due to this pi over here, and n being an integer, this equation is not quite fits in the definition of periodicity, because n has to be an integer and pi is not a rational number, right? So there is no way that this n could be an integer. So no way, you cannot find the small capital N to be an integer if on the right hand side you have a pi. Okay, so pi is an irrational number, so this is not periodic. There's no integer sample number after which this sequence is repeating, so this is not periodic. But if you want to find the period of, for example, this signal, this is periodic, you can do that. So for example, this is cosine of 2 pi n, and if I just add this plus n over here, right, n plus n divided by 12, then the constraint is that this will imply that if this is equal to, if this brings back my x of n back, then the implication of this will be that 2 pi into capital N by 12 should be equal to integral multiple of 2 pi k. Okay, why? Because adding or subtracting 2 pi in the argument of cosine doesn't bring any change, and still cosine theta, right? I mean, the idea what I'm doing over here is that since cosine, I know that cosine theta plus minus 2 pi k is again cosine theta, right? Is again cosine theta. So that's what's going on over here. So in order to check the periodicity, that my constraint for discrete time sequence is that capital N has to be an integer. Okay, so I need to find an integer for that. So 2 pi n plus n, then 2 pi capital N by 12 should be integral multiple of 2 pi k, should be integral multiple of 2 pi, right? And then you see this 2 pi cancels out, and you know that k is also integer. So capital N is 12k, right? Which means 12 is the period, right? It's also periodic for 24 or 48, let's say, but k is equal to 4. But the minimum period after which the number of samples after which this repeats is 12, right? It's 12. So and you can go on counting these samples. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, so for example, these many samples are what constitute the period, and you can count the number of samples. These are 12 samples, right? These are 12 samples. So n is 12. You can also always go ahead and find this integer. N is 12. But you cannot find any integer for this case. So the constraint is that you will see this in the literature further, that your digital frequency in radians divided by 2 pi should be a rational number. Omega naught by 2 pi should be a rational number. So let's say ratio of two integers, let's say k by m. So that means over here in this case, 2 pi by 12 is what omega naught is, divided by 2 pi is 1 over 12, right? So it's I mean 2 pi by 12, if you divide this by 2 pi, you get a rational number, right? Similarly over here, 8 pi by 31. So let's take this example. 8 pi by 31 is my digital angular frequency, okay, in radians. So if I have to divide this by 2 pi, I get a rational number. That is ratio of two integers. Okay, it's an integer by an integer, so that would be 4 by 31, right? 4 by 31. So again, I can find capital N to be an integer in this case, right? But for this case, where the digital frequency is 1 by 6, so dividing 1 by 6 divided by 2 pi is going to give me 1 over 12 pi. This 1 over 12 pi is not a rational number. It's not going to be a ratio of two integers. So therefore, this is not periodic again. So you see in all the discrete time sinusoidal signals, unlike continuous time sinusoidal signals or continuous time complex exponential signals, the discrete time sinusoidal signals or discrete time complex exponential sequences are not always periodic. This condition must be satisfied for all the discrete time sinusoids to be periodic, that their ratio of their digital frequency with 2 pi should be a ratio of two integers, or it should be a rational number. Okay, it should be the ratio of two integers. Okay, all right. So as before, what we can do is, if your sequence is purely the exponential sequence is purely imaginary, okay, the beta is purely imaginary, if it's in this form. So you can always expand this by Euler's relation, and it allows us to relate the complex exponentials and with sinusoids. So you can bifurcate this into cosine and sine, and then again you can write this in another form. So amplitudes again have a polar form like this. If you introduce in general the phase phi, which is in radians, okay, omega naught is in radians, n is again a dimensionless quantity. So you see the amplitudes again over here are complex, but the frequencies of these two terms is again omega naught. Okay, and for these two, for this discrete time sinusoid to be periodic, the condition will be that omega naught by 2 pi would be the ratio of n, ratio of two integers. It would be k by m. Okay. not otherwise. So the signal in the following equations are example of discrete time signals with infinite total energy but finite average power. So this statement is very similar to what we have in continuous time exponential signals. So that is that if you have to find energy, well, the energy of such a sequence, this sequence, is nothing but the magnitude of x of n. If you take the magnitude of it, square this, and add this, okay, over all n. So n from, let's say, minus infinity to plus infinity, the energy you can see is infinite, right? It's just like adding one infinite number of times will give you infinity. So it's not an energy sequence, it's a power sequence. Why? Because let's say I have this sequence, okay, and let's say, okay, n is from minus n to plus n, and I'm going to take, okay, let's plug this in. So this is e j omega naught n magnitude squared, okay, and what I'm going to do is for the power I'm going to take the average over the same number of samples, and I'm going to allow this n to go to infinity, and this way I'm going to cover the entire length of the sequence, all the samples. So this magnitude squared is 1, right? So what I have over here in the summation is 1, right? And I have to sum this up how many times from minus n to plus n, and if you have to count 0, well, this whole summation is nothing but 2n plus 1. So what you have is, and then, okay, if you're also allowing n to be very large, n to be very large, what you have is a ratio of 2n plus 1 or 2n plus 1, and that gives you 1. So you see the average power is finite, and that's unity in this case. So they are power sequences, they are not energy sequences. Okay, so for example, since the magnitude of exponential squared is 1, so every sample of the complex exponential signal contributes 1 to the signal energy. The total energy is infinite. Total energy is infinite. If you take the total energy over the entire length, you allow n goes to infinity, then it's an infinite energy sequence. While the average power per time is obviously equal to 1. So this is how it comes to 1. So again, these are the power sequence. They are not the energy sequence because total energy is infinite. Now, let's generalize the discussion of the complex exponential sequences. So in general, your magnitude c could also be complex, and if you express this in polar form, you see, if you recall, we are again discussing the form of the discrete time sinusoids, okay, and we said that c and alpha can take any value. So for example, c could be real, alpha is real, then we have real, we discussed 4 possible real exponential sequences where exponentially the sequence could be growing, it could be decaying, or the samples could be alternating. Okay, so there were 2 other cases as well. Now these were the 4 possibilities for c and alpha being real. Now what if in general c is complex and alpha is complex? Okay, so they have the real and imaginary parts. Now we are expressing c in terms of in polar form. Okay, so alpha is again complex. Okay, so so what you can do is you can have the magnitude terms together. You can combine them. Okay, and then you can go on expanding exponentials in the Euler form. So you have the real part as cosine and imaginary part as sine, with omega naught as digital frequencies having dimensions of radians. And if omega naught by 2 pi is a rational number, then it's periodic, otherwise it's not. We know that now. So if alpha, now over here is magnitude of alpha is 1. Okay, so what happens if magnitude of alpha is 1? Then that means we simply have sinusoids, right? For magnitude of alpha being equal to 1 simply implies that we are only considering magnitude c times cosine part and sine part. Okay, so this would be cosine of omega naught n plus theta plus j sine of same argument. Okay, so we're just having sinusoids in the complex in the real and imaginary parts of the sequence, right? So the real and imaginary parts of the complex exponential sequence are sinusoid. But now And this again is non-decaying, right? And for example, cosine can take plus minus 1, and this trend continues again. Sine can take the magnitude anywhere between -1 and +1. Okay, so these oscillations, they continue without being damped or growing. So, but if alpha is less than 1, then you can guess this, that the sequence is going to decay. Okay, so the corresponding sinusoidal sequence is multiplied by a decaying exponential, right? Because alpha is less than 1. So this alpha could be, for example, half. This could be half 1 to n. So the samples are going to decay like this. Okay, but again, in an alternative manner, I mean, the signs are going to be alternating. Okay, so we'll have the alternate, what you must say is, the sample, the sign is going to be alternating. Okay, if alpha is, I mean, it depends on the sign of alpha as well. Okay, but while for alpha greater than 1, they correspond to the sinusoidal sequence being multiplied by a growing exponential. Okay, so you can see this over here. You have a growing exponential, or you can have a decaying exponential. So this envelope of the sequence, this is the envelope, this is the shape of the samples, and this case is for alpha greater than 1. This is a growing discrete time sinusoid. Okay, so for alpha greater than 1, the sinusoidal sequence is being multiplied by a growing exponential. So the envelope is what you're looking over here, is that it's growing with time, growing with a discrete time index. Okay, because alpha, magnitude of alpha is greater than 1. And similarly, if magnitude of alpha is less than 1, then you have decaying. The oscillations are going to decay with the discrete time index. Okay, and the amplitude of the samples will be becoming small. Okay, with increasing n. So A is growing discrete time sinusoidal signals for alpha greater than 1, and then B is decaying discrete time sinusoid for magnitude of alpha less than 1.